Um, okay, why are these letters being used? I don't know. But the thing you need to notice on this is that the index is the same, right? So if you're multiplying values that have the same index, you can combine them into the same root with the same index. Now, if the bases are the same here, you can still, and this goes back to more exponent rules, but you can add those if you wanted to as well. You can do it this way. You can say, well, I'm going to take a to the power of j over m, and then this one would be a to the power of m. Oh, it's supposed to be an n. I apologize. Not n, not m, but n. It's supposed to be an n right there. See, and what happens here is that you can combine these bases by taking, because they have common denominators of n, and then just do j plus m. Now, whether you go this route, which then kind of leads back to this route, is okay. I think for the most part we kind of go this way, though. So we're looking to make these fractional exponents, and then we combine them if the denominators are the same. If not, we can force those denominators to match. So keep that in mind. This takes us back to some fraction stuff, which, by the way, the calculator will do. So at this point, if you saw you're just going to add the exponents, you can put it in the calculator. Even if the denominators don't match, it will give you the simplified fraction from that addition. Rationalizing denominators. So this goes back to, we don't want square roots or roots. We don't want any roots in denominators. So please do not put them there. But we can force them to go away on our own. So kind of like what we saw in that last one. But now it's not necessarily a principle of equality with these ones, but you just need to remember. So remember, let's go back to a common fraction like 1/2. So to rationalize denominators, what we're going to be doing is we're going to be multiplying something. And again, the process is essentially the same, but now the work, it's kind of different work, right? So if I wanted to scale this up, I could say, I just want 2 times 4 to get a denominator of 8, if I wanted a denominator of 8. But if you do it to the denominator, you need to remember to do it to the numerator. So notice it does not change the value of the fraction. It changed the way that it looked, but not the overall value. And that's the key part to scaling fractions like this. Now, with that, would that have mattered if I multiplied it by the square root of 4? It wouldn't. I mean, it changes the value. It's not now 4 over 8. You'd get something else, which we're going to get into. But to rationalize denominators, we're going to have to multiply these by square roots, both in numerators and denominators. That's what we're doing. Yeah, we're kind of like trying to find common denominators. What else does it say? You'll have to determine what to multiply the denominator by to make the radical go away. So you are forcing this to happen. You are taking control of a fraction and not letting it destroy your life. So this requires multiplying numerators and denominators. That's what I'm showing right here is in this example, and then making the exponent of the radicand match or be multiple of the index. The reason why that will happen, or why that's useful, is because we're dividing the exponent by the index, and if I can make that a whole value, all the better. So rationalize the denominator, no problem. What I need here is not a square root, right? In the denominator specifically. I do not want a square root in the denominator. Now this 13 is kind of a weird number, right? Prime. I don't know if that makes it pretty, but what I would like to do is to get that denominator to not be a square root. So how are we going to make that not a square root? I'm going to take that square root of 13 and just multiply it by itself. Okay, because the square root of 13 times the square root of 13, I can make that the square root of 13 times 13, which is the square root of 13 squared, which is just 13. So that makes the denominator just a 13. But don't forget, if you do it to the the denominator, you got to do it to the numerator as well. And now in the numerator, I've got 52 times the square root of 13. So I'm going to show that here, 52 times the square root of 13. Now, if the 52 and 13 can be simplified, then I should. And as it turns out, 52 is a multiple of 13. 52 divided by 13 is 4. So that part right there gives me 4. And then I still have multiplied by the square root of 13, and that would be considered fully simplified right there. Now sometimes students just stop right here. It's like, hey, look what I did, because we're not really familiar with, dividing by 13. Put it in the calculator, 52 divided by 13, and it'll tell you it's 4. So make sure to do that. Now, that's one way to do this, okay, and that's showing some work, which we like or don't. But what you could have done is you could have used calculator method on this one. I think. I'm going to try it. So 52, I'm using the N over D button, square root of 13, enter. Boom. They gave me 4 times the square root of 13.
Even on the exam?
You got to show some work on an exam, though. For these, if you have a square root in the bottom, usually it just kind of matches here. I had the square root of 13. I would almost always expect the new denominator to just be whatever was inside that square root. Now, you could simplify those if you wanted to, but usually if we just make a match, then we can kind of factor out from the top by itself.